Okay, so we have presented the outline of the class, but now we're going to start talking about the content of the class. And here we have an estuary, a typical estuary. So if there's a classification, a definition of an estuary, well, how would you define an estuary? Anybody? How would you define an estuary?
Mix of salt and fresh water.
Right, a region, right? A region where salt and fresh water get mixed. So that's a very important part in the definition of an estuary. What else?
A semi-enclosed basin.
It's a semi. So that region should be a semi-enclosed basin. Okay, so we have two ingredients now in an estuary, so that's good.
A place where the river and the ocean meets.
Right, so that when the river and the ocean meet is exactly where fresh water and ocean water mix. So we have that ingredient. We have the semi-enclosed body of water, and the third ingredient is that it has free communication with the ocean. So that's the definition proposed by Cameron and Pritchard back in the 1950s, actually. In the 1950s, it was proposed by Cameron and Pritchard. So those are the three ingredients of the original definition. But as the science of studying estuaries has evolved throughout the years, we've found systems that might not fulfill these three ingredients, but still they might be estuaries, or they might be considered estuaries. There's a colleague from Stanford, his name is Steve Monismith, who likes to quote his advisor, who's Hugo Fischer, who wrote a book on estuaries, that estuaries is like pornography. You know when you see it. You know one when you see it. So obviously that draws a laugh all the time, but so you know when you see one, right? Maybe. It's relative, but just keep that in mind, because there are systems like coastal lagoons that don't have any fresh water input that could maybe be considered as estuaries. For example, if there's a lot of evaporation in this area, there's no river discharge, there's no precipitation. What's going to happen to that body of water? It's going to become hypersaline, that is, the salinity of the basin will become larger than the salinity of the ocean. And what will that do? What will happen?
Because of the density variation, it's going to be a current against the
right.
less salinity.
So you'll have a circulation that's opposite to typical estuaries, and we'll see what the circulation in typical estuaries should be. But importantly also, in these coastal lagoons, well, what I was going to say about the salinity, when I say hypersaline, what do I mean? Does anybody know? What's the average salinity in the ocean? 35, right? Do we know that? Do we remember that? So 35 is the average salinity in the ocean. When I say hypersaline, it means that the salinity in this lagoon can become what? 36, 37, 40, 45. Does everybody know the salinity of the Dead Sea? I don't know, but it's very large. It's around 200, I think. But so that gives you an idea. Right? The salinity of the ocean is 35, which means that approximately 3.5% by mass of an element of water in the ocean has salt. All right, so let's see how we can classify estuaries. And there are different ways of classifying estuaries. One is according to their origin, and in particular their geologic origin. So in terms of their geological origin, we can have, I should use this because otherwise it won't get recorded. We have this Drowned River Valley, where you see a cross-section. If you go along line A to B, you see this cross-section, a profile view. So you can see how there was a river there before the Pleistocene. When was that? The Pleistocene. When did the sea level start coming up in this post-glacial era in which we live? Before this era, in the glacial era, well, there was a lot of ice, right? There was much more ice around the poles than what we have today, so the sea level was lower. And 15,000 years ago, the Pleistocene, that started melting and sea level started going up, and it inundated river valleys. So that's why they're called drowned river valleys. Does everybody know of an example of this type of estuaries where river valleys got inundated by sea level coming up? The essential example is the Chesapeake Bay, but there are several here on the east coast of the U.S. There's the Chesapeake Bay, which is the prototypical example of drowned river valley. You can imagine how there was a river there, and when the sea level came up, it inundated. North of the Chesapeake Bay, you have what? Does anybody know what this estuary is? Delaware Bay, that's another drowned river valley, and also a small one here, a narrow one, the Hudson River estuary is also a drowned river estuary. So that's one type of estuary, the drowned river valley. The other one is the fjord. And also, the fjords got inundated with sea level increase, but the particular characteristic of fjords is that they're deep, so they were glaciers. Imagine the glaciers that we now have in Greenland, that they're melting. So imagine those glaciers. If sea level was to increase dramatically and get to those glaciers, then you'd have deep basins that have been carved by the glaciers as they move toward the ocean. So those basins, as they're inundated, those are the ones that are the fjords. And usually fjords, if you look at a cross-section, if you go from A to B here, which is this profile, fjords are usually characterized by this moraine. The moraine is the end of the glacier when the glacier was active. So that's where the glacier deposits most of its material as it advances. So you have a sill that separates a basin, the fjord, from the adjacent ocean. So again, fjords are typically characterized by a sill. And if you look at a cross-section, if you go across the line C to D, you have these steep walls. Because again, that's the glacier. So it's like a river that's very erosional, that's carving the walls and the bottom. So that's how fjords are created. You have spectacular views in fjords. These two are from southern Chile. That's where I'll be next week. Does anybody want to go? The third type, so we have the drowned river valley, we have the fjords. Remember, we're talking about on the basis of their geological origin. The third type is the bar-billed estuary. And these were created by littoral transport. You have a sand spit being formed along the coast. And many of you know sediment transport much better than I do. So you can tell me how that sand spit can be formed. So say you have an embayment first, and then you have some sort of sand transport that forms that sand spit. How could a sand spit grow from an embayment? Can anybody illuminate us? Come on, don't be shy. I know that you know these things better. So if I tell you anything, you'll accept it, huh? No? Anybody? Nobody. So you know how longshore sediment transport occurs, right? How do you develop a longshore sediment transport pattern?
direction, which direction waves are going in.
Yeah, the incidence of the wave, right? So speak loudly so that our Korean friends can hear what you say. Yeah, so the longshore currents are formed by the angle of incidence of the wave, as you well know. So that might create a separation of the sand from the coast and create a sand spit. So that sand spit will isolate effectively a coastal body of water if there's some river coming in. Many times this sand spit can be from the material that the river deposits to the coastal area, and then the waves just redistribute the material and create the sand spit. Sometimes it's a material that's from the beach already, and it's transported along the shore. But the thing is that you end up with systems like this, like the ones on the photographs, where you have a bar and an inlet, like Ponce de Leon, like St. Augustine Inlet, and like the one that we'll see also in St. Andrews Bay. Similar situations in which they're all bar-built estuaries. Because you get a sandbar that forms the coastal body of water. So that's the third type of estuaries, and the fourth type is the tectonic type of estuary. And again, the typical example of tectonic estuaries is San Francisco Bay. San Francisco Bay, once you have a fault because of tectonic activity, you get the formation of a water encroachment to the coast, and you get the San Francisco Bay. Any other examples? Peng, what other examples did we discuss? Do you remember? I think there's another example in the Baja California Peninsula. It's not on the peninsula, it's on the mainland side of Mexico. It's called Guaymas Bay. And somebody else gave another example. Can you think of a tectonic area where you have a coastal body of water like this in San Francisco Bay? How about northwest or southwest Canada? Any like that?
I can't think of any. Sorry.
They're all of fjord origin, right? Oh. Is that what you said? Also, you need to speak up not only for the microphone, but hearing is not very good. So those are the four types of estuaries according to their origin. So another type of classification is based on the stratification of estuaries, on how stratified they are. And to understand that classification, we need to understand what happens in estuaries typically. So we have this simulation. We'll go to a virtual laboratory now, and we're going to put light water on the right in blue, and heavy water on the left in red, separated by a wall, a partition initially. So when we separate this partition, what's going to happen to these waters? That's right. Exactly. Heavy water will go down. Heavy water will flow down in that direction, and light water will. Sorry, which one was heavy? This is heavy, and the light will go that way. So light water will go that way, heavy water will go that way. And I'll describe it like this because I haven't figured out how to record these animations for our Korean friends. So they're not able to see this. Oh, we're not able to see it either. Maybe because of the program. So maybe I should turn the screen and you'll see it. Can you see it? So we have the red who's the heaviest. That is the heaviest, and the blue that's the lightest. So that's what you'll have in the long run. That's what you'll have in estuaries. Right? The light water from the river tending to go out at the surface, the heavy water from the ocean tending to come in underneath. And this is what's called the estuarine circulation, typical estuarine circulation, the two-layer circulation. So whenever I refer to estuarine circulation, I'm talking about this type of two-layer flow. Or gravitational circulation also, because it's an adjustment of this pressure gradient under the influence of gravity. right? Initially there's a pressure gradient, light water, heavy water. The surface, what happens to the surface elevation when you have light water and heavy water? Which is taller, the light water or the heavy water? Just based on hydrostatic. Light water stands taller, right? Okay, that's the only animation for today, so that's good. Glad that we don't need to deal with other one. So that estuarine circulation will tend to cause stratification in the water column. Heavy water near the bottom, light water near the surface. So we can classify estuaries according to their stratification. And this really results from the competition between tidal forcing, between how strong the tides are at the mouth of the estuary, and the buoyancy forcing, how strong is the river input into the system. So in this type, the salt wedge estuary, we have 3 stations along the estuary. This is a plain view. And we have station 1 close to the river mouth, station 3 close to the mouth, to the estuary mouth. So you can see near the mouth of the estuary, the salinity is very low, practically zero. It's all river water. And at stations 2 and 3, you have a very strong stratification. A uniform layer of low salinity water at station 3, very sharp interface. How do we call that interface? This interface. In the case of, we're talking about salinity, so this would be the what? The what line? The halo line, right. And then if we move further to the ocean, we have these 3. The surface layer is thinner, and we have this halocline again. So the bottom layer is relatively uniform. And what happens, the circulation associated with a salt wedge type of estuaries, you have a surface layer that's causing net outflow in the F direction, and a bottom layer that's causing inflow. But the inflow is relatively weak because you only have inflow of heavy water during the flood portion of the time. So the salt wedge type of estuaries can also be referred to as strongly stratified estuaries, right? They're very strongly stratified, very sharp haloclines. So these are very fascinating to measure because the gradients, the vertical gradients, are huge. Imagine the salinity at the surface would be around 0, close to 0, 1, 2, and then near the bottom it gets up to 30. Does anybody know an example of this type of salt wedge estuary?
The Fraser River.
The Fraser River. That's right. The Fraser in British Columbia. I wonder why you know that. Any other closer to home? Actually, the river goes by the home of the newly crowned champions in football, college football. So that's the Mississippi River. He said it. He didn't want to say it loudly, but the Mississippi River, which goes by Baton Rouge and ends up in New Orleans, that's a salt wedge type of estuary. If you go if you go and make measurements near New Orleans, you're going to see this type of situation, very sharp gradient in the halocline.
So what causes that? What's the difference between that?
Okay, yes, good point. I hadn't mentioned that. So notice here on this side, we have the river discharge is high here. So in the case of a salt wedge estuary, the river discharge is high. The tidal mixing is minimum, very weak also. The tidal currents are weak. And so the stratification is strong. So remember that the stratification will be a competition between tidal forcing and buoyancy forcing. So if the river discharge is large, we know that the Mississippi River is the largest river in the U.S. in terms of the freshwater discharge, right? Does anybody know how much? No? No idea if I told you 1,000 cubic meters per second? Yes? 1,000 cubic meters per second is very small. Well, not very small, but it's small. So the average discharge, the average annual discharge for the Mississippi is close to 30,000 cubic meters per second. So that just starts to give you an idea. In comparison, the Chesapeake Bay, which is the largest estuary in the U.S., the largest estuary, not the largest river. The Chesapeake Bay receives an average of 2,000 cubic meters per second versus 30,000 of the Mississippi. So that gives you an idea how much water the Mississippi. Well, think about where the Mississippi comes from, and all the water that it collects along. So going back to the question, you have very high river discharge and no mixing. So the fresh water will slide very nicely over on top of the heavy water. You create a density gradient, as we saw in the simulation, and there's going to be very little mixing between the two, so they will slide between each other very nicely. So the salt wedge type of estuaries, that's where the name comes from, the salt wedge, because you create a salt wedge that slides underneath the light water. Then when river discharge starts to decrease and tidal mixing starts to also increase a little bit, as well as the tidal currents, then the water stratification starts to decrease a little bit, like in this case of a partially mixed estuary. So you have, as you go along the estuary, you have the river mixed with low salinity water, sorry. And then you have some stratification here in the middle of the estuary, and closer to the mouth you have some stratification, but still the Halox line is weak. And I was asking you about the Halox line. I didn't notice that it says that. I usually ask those questions, right? And you have the answer. Right? That's why you don't want to say the answer, because you have it right there. And the circulation arising from the interaction of the low density water with high density water under moderate mixing, as in this case, is a more vigorous exchange. So why is that? Because the mixing increases the longitudinal density gradients. So that favors this exchange. Notice this, although this is a schematic, it also happens in reality that you have a stronger inflow in the partially mixed estuaries than in the salt wedge estuaries. On the average. Okay? One very important concept that I want you to understand here is that what this circulation represents, what this diagram represents. This diagram represents average conditions after you eliminate the effects of the tides, after you average out the effects of the tides. So when you go out to the field and make measurements, you will rarely see this type of circulation. You will see the tides will mask this type of circulation. So after you average out the tides, you will see this type of circulation. Does that make sense? So at any given time, either the flood or the ebb of the tide will dominate the flow, as we saw very nicely in Ponce de Leon and in St. Augustine, that the tide dominates. But on average, you might have something different, or you will have something different. Yes?
Actually, we are talking about all the time the fresh water and the salinity of the ocean. However, isn't the reverse might be the case sometime? For example, Yellow River, discharges into ocean,
right?
Because it's in terms of sediment concentration.
That's right. We'll get there.
Oh, okay.
So those are estuaries also, but how would you call them? Inverse? Inverse estuaries. We'll get there. And then another type of estuary on the basis of its stratification is the well-mixed estuary. And you see that you have variations both along the estuary, that is from 1 to 3, if you follow the middle diagram. Salinity at 1 is much lower than salinity at 3. But also there are lateral variations of salinity. Salinity at 4 is greater than salinity at 5. Why would that be, you think? That salinity at 5 is lower than salinity at 4.
Coriolis first?
Yes. So it has to be this has to be in the northern hemisphere, right?
Yes.
What if it was in the southern hemisphere? Salinity at 4 would be lower than salinity at 5. Right? So usually many of these examples that we'll talk about in this class are biased to the northern hemisphere. So just keep that in mind. And usually researchers from the southern hemisphere feel discriminated, and they always protest when they see something like that. So I'll try to remind you every time. I'll try to remember myself to also talk about the southern hemisphere. So in the case of a well-mixed estuary, you don't have a two-layer type of circulation, but you have the inflow developing over one side of the estuary and the outflow developing on the other side of the estuary. Although it says there, where do you think the inflow appears, on 4 or 5? Inflow appears at 4 because of Coriolis, right? And 5, at 5 you have outflow. So you have high salinity at 4, and that's where the net inflow develops. And you have low salinity at 5, and that's where the outflow develops. Vertically, not homogeneous, but in the same direction. Sort of a Couette type of flow. Remember your fluid mechanics class, Couette flow, the strongest at the surface and decreasing with depth because of bottom friction. Okay, so those are the estuaries based on stratification, according to the stratification. Let's look at a few other examples based on stratification. So you have the typical condition in a fjord here with the silt near the mouth. So you have outflow near the surface and inflow at depth, as depicted by the arrows in the diagram. And notice that the net velocity profile would show strong outflow in a thin surface layer, and very weak inflow in a very wide bottom layer. Why is this distribution like that, you say? I mean, this is analogous to the salt wedge type of estuary in the sense that it's strongly stratified, very strongly stratified. But fjords are much deeper. So why do you think you get this type of circulation?
Because there's a barrier. It can't flow out deeper than a thin layer at the surface.
The seal is very important. The bar is very important at the mouth, so it has something to do with it. But the surface layer, how much does it mix with the lower layer? If it's a deep system, there's very little mixing. So the surface layer just flows out, and that's the surface layer that flows out. And then there's the inflow is distributed throughout a very deep layer. So the transport, if you integrate it over the layer, it'll be significant, but it's distributed over a very large depth range. So it's going to be weak. The typical profile would be something like that: a surface layer that's stratified, as you can see here, surface layer that's stratified. So the whole surface layer is a pycnocline or a halocline. And then underneath the pycnocline, at the base of the pycnocline, you have a relatively homogeneous water column. More diagrams of the same concepts. There's the salt wedge estuary, so that you can see it in a schematic way, how the salt wedge intrudes, and there's a point where it can't intrude any further. Usually there's a shoal there where the sediment gets deposited and in turn hinders the progression of salty water in. The fresh water is going out at the surface, and there's some very little mixing between surface and bottom waters. And remember the competition between tidal forcing and buoyancy forcing. You have the small tidal forcing at the mouth and very large input at the head. An example of this is the southern hemisphere example. Where is that? Oh, there it is. It says there. This is the Rio de la Plata estuary in Argentina. So what country is down here? Right here.
Brazil?
Huh?
Brazil?
No.
Argentina.
Argentina. How about here? What's this? It's a small country.
Peru.
No, Peru is on the Pacific. This is Uruguay. Have you heard of Uruguay? Right there. Brazil is up here. And Paraguay is right on there. But anyway, these data are from a transect, a long estuary transect, approximately here, where the arrow is. And you can see there are sections of density on the left and salinity on the right at different times. Okay, so we have values of density anomaly here. What does this mean, density anomaly? I think I've asked you this before to some of you. What does it mean that we have values between 0 and 24 for density anomaly?
From fresh water.
Right. So it's the anomaly relative to fresh water. So a density anomaly of 24 means that water weighs 24 kilograms per cubic meter more than fresh water. And similar density anomaly of 4 means that a cubic meter of water weighs 4 kilograms more than fresh water. So you can see, well, if I show you that in what direction, to the left or to the right, is the river, by looking at those diagrams. Left? I hear left. Does everybody agree that the river is to the left?
Yeah.
Right. Even though we're in the southern hemisphere, the river is coming in here. So, and then if we go to the map here, if the fresh water is coming like this, where should it go because of Coriolis? To the left. It should go this way, right? And yet in this satellite image, you can see this light blue area is suspended sediment, and it's going to the right. So this is likely in this system. This is opening a parenthesis. In this system, in the winter, the winds blow from the south, so that would create the light water to go to the north in the winter. But this picture is probably from the summer, when the wind blows from the north and pushes the fresh water toward the south. So Coriolis, in this case, Coriolis is not important in determining the fate of the fresh water discharge. Okay. Closing parenthesis. We'll come back to that later in the course. We're looking at the cross-section, the longitudinal sections here of density, with the light water, a thin layer of light water going out. And you can see the salinity value around 3 or 4 at the surface and close to 30 at depth. Over a 10-meter depth distance, vertical distance, you have a very sharp density gradient. Do you remember what we have? The largest gradients that we observed last year. Not last year, last semester. What it was last year? Last semester. Difference between surface and bottom. It was in St. Augustine. 3 maybe was the largest. Or what did you say? 5? Well, maybe 3 or 4. Notice here you have differences of more than 20. So that gives you an idea. Over the same depth range. So that gives you an idea of how strong. The river discharge here, given that we have a salt wedge estuary, you say that the river discharge is large or small? Large. So it's comparable to the Mississippi, actually. So it's that large. So they compete to see which one is the 3rd or 4th largest in the world in terms of river discharge, the Mississippi, or 4th and 5th, something like that.
And if we fix with just the river discharge on 1,000 cubic meters per second, if we fix the other variables in the before slide, we just change the river discharge, then what about the rest?
Here?
Yeah, this one. We have 3 variables, right? The river discharge and tidal mixing and tidal current.
Right.
So if we fix the tidal currents and tidal mixing, just change the river discharge,
Right.
then which one has more
what do you think is going to happen? Say in the salt wedge estuary, if you fix the tidal forcing, but you decrease the river discharge, what's going to happen? Yeah, the salt wedge will remain, but the salt intrusion will go further up the estuary. So the salt intrusion will be much higher up.
And just to remain that distribution.
Maybe. If the tide is strong enough to mix, because the gradients, also the vertical gradients will decrease when you decrease the river discharge. So the vertical gradients will decrease, so the tides might be strong enough to start producing some mixing. Right? So something that I want you to keep in mind about these classifications is that they're sort of, in my view, they're arbitrary because there are systems that change from one type to the other within one tidal cycle. Not only from month to month or from season to season, but within one tidal cycle, one system can change from one type to another. So just keep these classifications in mind loosely. We're going to talk a more strict classification once we learn about the dynamics later on. But that's a good point. Okay, so there's the example of the salt wedge, an example of a fjord type estuary, and with strong stratification. We're looking here at this orange line that you see here, starting from here. This point in the transect, do you see the arrow? Is the leftmost point here. And this point in the orange trajectory, this point right here, is here at the right. Right? So, and there's this very shallow seal, which is right here. You see in this photograph, you can even see the change in color, right? In the color of the suspended material. You see, it's the water seems to be more milky on the left. You see that? You can see where the fjord is down here. It's in the Strait of Magellan. So see the yellow arrow right there. The Strait of Magellan is here, like this, and it goes like that. The famous Strait of Magellan. So anyway, here are data of salinity, temperature, and density anomaly. Cross-section depth versus distance, only the first 20 meters. The black dots represent the location of measurements. And you can see the very thin fresh and cold water that's light, like 5 meters deep, and you can see continuously stratified, and then below that, very weakly stratified, almost uniform. The very interesting aspect of this is that you have low salinity water and low temperature. Why doesn't it turn around? Low temperature. Is low temperature water heavier or lighter than high temperature water? I think you said it right. I don't know what you said, but light water is warm, so it's lighter. Light water is warm, and heavy water is cold. So, but here we have low temperature water at the surface. That's because it's much fresher. So the salinity is the one that determines the density. But the interesting thing is, where is this cold water coming from? Why is it cold at the surface? Any idea?
Air temperature.
Sorry?
Air temperature. Air temperature.
Air temperature? It's a possibility. It's a possibility.
Snow melt.
Right. Snow melt. That's a possibility too. That's a good possibility. So those are good explanations. Those are good possibilities that happen elsewhere. But here we are.
Like glacier.
Well, I didn't tell you. There's a glacier here. There's a glacier right there. So this is glacier water that's melting. And when the glacier water melts, it's low salinity water, very cold, low salinity, where it goes to the surface because it interacts with the salty water. So it goes to the surface immediately and tries to go out. So that's how this fjord circulation. Okay, so let's take a quick break here.